Welcome to the sixth part of the tutorial. This part is dedicated to PY-PDB, the section of the website that can be used for key-lock association of proteins and small molecules, which is essential for building your structure-based models. Starting from where we left off, go back inside your dataset. Now scroll in the left sidebar and find the Add a PDB button. Now you need to find the PDB code of the protein you want to import inside the dataset, as this will be the target for your molecules. You can look for the code on Protein Data Bank. You need to find the exact protein. Be careful, because they can differ by animal species. What you find on Protein Data Bank is always a crystallized protein ligand complex, so there will be your protein associated with a small molecule. This is very useful because the ligand is already correctly inserted in the protein pocket. We will use this for the docking validation in the next part of the tutorial. Now copy-paste K4 characters code inside the text box and press Submit. Now the site will download the protein complex for you. Click on the search box and press Start repeatedly for refreshing the status of the operation. If the operation fails, that means the complex on Protein Data Bank can't be downloaded, so you need to download manually and clean on UCSF Chimera, then import in the site, as we will see later. Okay, now that the downloading process is complete, you can press on the Clean Base text on the right. This is the protein cleanining page. Here you need to remove redundant chains and ligands used from crystallization from your protein complex. First, leave only the main chain selected. Check in Protein Data Bank which is 1, and if your protein is monomeric or dimeric. In this case, it's monomeric. Now leave only the interested ligand, which will be a small molecule similar to the ones inside our dataset. Remove the glycerol molecules which are not essential. Some enzymes require water to work. In that case, don't remove it. To know what are those names, the A stands for chain A interaction, B stands for B chain interaction, and FDR.1A and GOL-1721.A are codes you can find on the Protein Data Bank page. In this case, FDR is our small molecule ligand and GOL is glycerol. As you can see, there is a second FDR for the B chain, but we don't need it. Now select the ligand, as we said before, FDR for the A chain, so A FDR. Now select cofactors or substrates if there are any, then press Submit. Protein cleaning will take a while. Wait patiently. Okay, now press on View/Minimize. Protein minimization re-adds hydrogens to the residue of the protein and resolves steric crush. You can activate the solver to simulate water. This can change the conformation of the protein a little bit. Refrain from doing this if your protein is an ionic channel, as it will never complete. Now that it's completed, go under here and press on Save to save the lock and key unminimized complex. Then click on View on the minimized complex. Then save the lock and key of the minimized complex. Great job! This will add the small molecule to your dataset, as you can see here. If automatic retrieval or cleaning of your PDB failed, download it manually from Protein Data Bank like it's shown here and execute the cleaning procedure on UCSF Chimera. Select the redundant chain and delete it by activating the command line and executing the command delete selection. Then under residue, select glycerol and water and delete them. Now delete the ligand so you can export the protein alone in a .pdb file. Now reopen the complex downloaded from Protein Data Bank. This time, delete everything but the small molecule. Save it in .mol2 format, as this will retain its three-dimensional positioning relative to the protein. You can load manually the .mol2 molecule in the dataset using pi-moledit, like we saw in part 1 of the tutorial. To import the protein, you need to go press on My Targets button. Then add a target from a file. Select here the .pdb file created with Chimera. Now you need to change the target of all your molecules to your protein. Use this selector here. If you manage to minimize your proteins, set the minimized lock as target. Great job! Now you are ready for molecular docking. Stay tuned for the next part of the tutorial.